Okay, so tonight is going to be object-oriented programming. One quick announcement before that. One of the assignments this week is to install Visual Studio on your local machine. For the last 2 weeks, we'll be using Visual Basic and putting GUIs together with Visual Studio, which makes it really, really easy. Then we just drag our mouse around and put the graphical user interface together. However, it's time for a new computer, and I only have about 12 gig left on this computer. So I'm going to have to access the school's machines remotely. So for the lectures, when we get up there, I will be using remote access to the computers in the labs at school to go over Visual Studio stuff. They are installed on there. This computer is coming on the end of its life, and I could probably delete some stuff and make it fit. But Visual Studio is huge, powerful software, so I'm a little worried about running that on a computer as compared to like just the old text editors like we've been using in Python. Those don't take up quite so much memory, so I'm a little worried about the old computer crashing when I install Visual Studio. So I'm just going to, there's Jerry. I'm going to stop the screen share to make sure it lets him in. Hello, Jerry. How you doing?
I'm doing good. How you doing?
All right. So we were just getting started here. I was talking about one of the assignments this week is to install Visual Studio, which my computer is coming on time to replace it. And Visual Studio is big, powerful software. So I don't mind running text editors on this old laptop, but I'm a little nervous about the big fancy IDEs right now. Like I could fix anything that happens, but I very much expect crashes to happen on my old computer. So when we do the Visual Studio lectures, I was going to be accessing the school computers remotely and just using Visual Studio there. So if anybody else wants to do that instead of installing it on your own computer, which obviously it's time for a new computer, but I'm thinking I might get a Chromebook because I'm seeing those more and more, and can pick up Chromebooks cheap, and I want to pick one up and at least spend a month learning the operating system really well. That way, if people have questions or something, I know a little bit more about Chromebook and can help people with those. Those have been showing up more and more. So my first replacement on this old laptop is going to be a Chromebook, so I wouldn't really be able to run Visual Studio if I do that this weekend anyway. But if we go to the video lectures section on Ivy Learn, I put the instructions on how to remotely access the school's computers here. All the way at the bottom, there's a little video walking you through the process, or the written instructions, which are very easy to follow. I just thought I'd take a moment and go over that here before we get into the object-oriented programming stuff tonight. So to access the school's computers remotely, there's a PDF on there that has the instructions. Basically, it's just follow this link and make sure you use SAML authentication instead of a regular login. And it will remember you the very first time. You'll have to enter, it'll go to the regular Ivy Tech login, which I'm sure everybody's seen many times. The green screen, the standard Ivy Tech login. But once you log in that, you'll get to this page, which shows all the computers up at the school that are up and running. And if you are familiar, room 158 and 162A, those are our labs for the School of IT. We have our own network and stuff there. So you can just click on that to see what the computers in that room, and any of them that are turned on, just hit the button jump to access it. And it'll just take a second. And then going on there? Is that my keyboard doing that? Okay. I'm not sure why that's going on. I think maybe one of the keys is sticking on my keyboard. But whenever you can see that's one of the computers on the school's flash. Why is the backslash key sticking on my keyboard? Oh, well, that's probably there at the, there might be something sitting on that computer there at the lab. But you can just jump to one of the school's computers and just use them remotely. So when we do the Visual Studio stuff, I'll be doing that for the lecture instead of installing it on my Lenovo laptop here. So I just wanted to mention that. And if y'all would rather do that instead of installing Visual Studio on your own machines, obviously I'm planning on doing that on lecture, so it should work fine for you. But those instructions are there on the page with the labeled video lectures. All the way at the bottom, just hit that PDF and it describes how to access the machine. And then once you get on, it's like you're working on that machine, just accessing it remotely. But that is still ahead of us. That's in week 7 and 8. We'll be doing Visual Studio stuff. So tonight we're going to get started talking about object-oriented programming. What you can see is kind of a long name. So the common abbreviation for that is going to be OOPS, obviously object-oriented programming, and then we typically just add the S on to make it a common word to say. It almost fits nicely with programming too. Calling something in programming OOPS. So we're just going to introduce it, kind of look at it, some of the main concepts, and then we'll look at some examples of doing it in Python. Just introducing it here, and for those continuing with programming in your 200 level class, that is over half the class will be focused on object-oriented programming. So the 200 level class is where you're really focused on doing it this way. And the quick way I like to describe it is we get to think like a human again. So I'm going to draw 2 pictures here. The first one, hopefully you've seen this before in biology class. Has everybody had a biology class before, like in high school or something?
Yeah.
So at least remotely familiar with the way humans classify things. Because the way biologists have chosen to do that is what's very natural for humans. We have this cascading levels where things get more detailed as we describe parts of life. So up at the top is just life in general. That's the most basic description of everything on Earth, right? And then there's 3 main branches that come out of life. Bacteria, Archaea, and Eukarya. And each one is a little bit more specific. They're distinctly different from each other, but they are all still just forms of life. And we're just adding layers of adding layers that get more specific as we go down. And if we continue it down, there's different types of Eukarya, such as like fish and reptiles and mammals. Obviously, I'm doing this I'm going to get very generalized here because this isn't a biology class, so kind of skipping the Latin names and flipping back to the more the regular English terms for them. But Eukarya splits up into these different branches that are all distinct from each other, but they're also still types of Eukarya, which are just types of life in general. And then mammals, we split that up. I'll just do a couple branches here. One branch of mammals would be humans, and another branch may be elephants. Is everybody kind of familiar with that classification system? It's very generic the way I drew it here, but hopefully everybody's seen something like that before.
Yeah.
And this is how humans naturally categorize things. So to start it, if we were doing some object-oriented programming stuff and went to diagram out the programs, the files and programs we have to work with, it looks almost identical to that. So it's like we're thinking like human. Up at the top is this generic thing called object. Everything in Python it's object-oriented language. Everything we've been working with so far is object-oriented programming. So this isn't something brand new. We've already been using object-oriented programming. We've just only been using pre-built objects and not really treating them as objects. So now we're going to get into treating them as objects. So what I do on here, animals. So there are different types of objects. Maybe we could represent a car object, which that's actually your homework for this week. And by the way, if anybody's interested in game development stuff, that car object that is your homework for this week, and that module I use to introduce pip for installing modules in Python, the Pygame, I'm almost positive that car object that our textbook uses is one of the standard examples that comes with that Pygame module for developing video games that they put together way before this textbook was written. So the car object you develop in this for this week's homework with just a couple more lines of code, it's only missing like 4 lines of code to be used in a video game. And it's actually the slightly larger version is in that. There's an example in the Pygame modules we installed. But sorry, just a little sidetrack. So we could define programmatically some sort of program that represents a car, the things about a car. You know, it's going to have a mast, traveling at some speed, the direction it travels, and everything we need to describe it. We'll talk about that in a little more detail later. I just wanted to draw some pictures. What else did I put on here? Maybe shapes, like math class geometry problems. We have a bunch of different properties of shapes, things that they would like all our geometry shapes would have in common. And then we could, same way this diagram goes together, we could get more specific and out in our room for words, but draw like a square or a triangle shape and have all the things about a square represented programmatically in this object. And that's an important part we'll talk about in a moment. Everything we need about a square is included in that object. So if we want to do any sort of programming that involves a square, we can just ask for this object that already has all the code we'll need to work with a square. Or the main example, when we get to one tonight, I'm going to do animals. These are kind of the 3 examples I always use whenever for the class lectures, and I alternate between them. I think I did shapes last time, so I'm back to animals this time. And we have some general descriptions of animals. The ones we're going to do in our example tonight, they're not going to have a whole lot to it. We'll put like a name, age, maybe how much it weighs, a method to make a sound, which will just echo a string back to the thing. But the general stuff that all of our animal objects are going to share, and then we get more specific versions and have like a cat object or a dog object. And then the dog object has, I said one of the things was a sound. So we add all the basic animal properties, and then the dog object we could add specifically makes the sound woof or something. And then we could just keep getting more specific and add objects to programmatically represent things we would want the dog in a program to do, with more specific types like a black lab or a beagle. And I know it's kind of jumping ahead here, but I like to start with these pictures because you can see the way humans naturally categorize things. We're getting ready to do that in our programs now, which is really nice after all, because everything we've seen so far, we have to kind of adjust, right? The machines don't process in the same manner as we think. And machines are not intelligent, we're the intelligent ones, so we have to adjust our thinking to match what the machine needs. But when we get into object-oriented stuff, we can kind of think more like a human again. That's why I like to just start off with these two pictures, because you can look and see when we categorize our object-oriented programs, it goes together the same way the humans naturally categorize things, such as in biology class. And yeah, we get to think like a human again. Once we have our objects put together, the interaction between them is kind of thinking like a human again. After a little bit of practice, which obviously is just being introduced in this class, so maybe not by the time the semester ends, we can go a little bit further and do some more stuff with object-oriented programming. It'll start to feel more natural, more instinctual in how things go together. Is it okay if I erase these pictures now?
Yeah, you're good.
Okay. Yeah, that's kind of jumping ahead because we haven't explained what those circles in that picture really meant. I like to start with that. So now we'll get into talking about what those mean. Well, some background. This was originally invented back in the early 60s. It was really well refined by the middle to late 60s, by 66, 67, 68. Everything in the design had been worked out. But computers could not handle it. Object-oriented programming is good for a human. It's bad for a computer. So we lose a lot of efficiency with it. But at this level, that's not really one of our concerns. If you continue further in programming, just be aware that we're losing efficiency with object-oriented programming. So we try to work in tricks to buy it back. And we don't lose up a lot of efficiency. So I'm just going to make up some numbers here because it's really, really good for the human. So if the programmer can do 1,000 times more at a 10% loss in efficiency, that's like plus 1,000 minus 0.1 for a 10% loss in efficiency, we're still coming up, 999.9. We're still coming out way ahead. And then that extra work is just passed on to the machine. We don't really worry how much work we pass on to the machine. So the programmer is allowed to do the programmer can do a lot more. It's good for the programmer. But still, and if you continue on, it's still nice to buy back some of that loss in efficiency when we can. Because a loss in efficiency translates to time. And as we write bigger and bigger programs, those losses of efficiency mean the program's going to take longer and longer to run. So it was invented back in the 60s, but computers couldn't handle it. But by about mid-80s, 1985 or so, the average computer could easily handle that loss in efficiency. And since then, object-oriented programming just kind of took off and has become the standard. So we mostly work with object-oriented programming anymore. So there are three key concepts in object-oriented programming. Three key concepts. And for us here at the introduction level, we're really going to pay most of our attention to number one. And then in the 200 level class, when you study this a lot more in depth, you'll look at number two a lot more. And if anybody's in like the SDEV program, after you finish your 200 level language specific course, you'll probably take something like mobile app development. And in that, you'll look at the third part in a lot more detail. For us, the first of the three concepts is the one we're going to look at the most, and that's encapsulation. I always hone in on the middle of this word. Encapsulation seems like the main part of that is capsule. Everything about this object is included. Like I use the example of a square object. And if we need to do some geometry in our program, everything we would want with a square, we'd want included here, right? In that bubble, we'd want everything we know about a square. So like the side length, have the area in there, some stuff about the perimeter. If we're gonna do a picture of it, what color is it? Is it filled in, or do we just have the outline? And all of the stuff that we would ever need to work with about a square needs to be included, like a enclosed capsule, and that's encapsulation. And yeah, everything we need is included, and we don't have to modify this. We're going to talk about it. Oh, it's on the next page. There's something called the open-close principle, which is on the next page, so it's going to make the board in a moment. But this program that represents a square is open for expansion, but closed for modification. So once this object is created, it cannot be modified. We can extend it as another copy using our second principle we'll get to in a second. We can extend it and add some functionality to it, but what's here is closed, so it can't be modified. And at the same time, that can also be taken as we don't care what's here. We know this represents a square, so we just ask for a square, and then the parts of it we need are included in there. So it's almost like thinking like a human again, right? Most people don't know everything about how a car works. They know how to make it speed up and slow down and turn, which is enough, right? Most people don't need to know all those fine details of the internal combustion engine and transfer casing and gear ratios in the transmission and differentials in the axles. Most people don't need to know that. Only mechanics need to know that part. Most people just need to know how to turn the steering wheel and which pedal makes it go, which pedal makes it stop. Just how to use it, not how to, not all the internal workings. So that our object-oriented programming is kind of the same way. We just need to know how to use it. We just need to know how to use it. We're not concerned. We don't need to concern ourselves at all with the internal workings of it. And that's encapsulation. Everything we need is going to be included. Ideally, because obviously we can't foresee every single case. But I just mentioned we can expand it. And that's the second of our principles, is inheritance. While I have this picture up here, well, the definition of inheritance is an object can pass its methods, attributes, which I'll here in a moment, I'm going to start calling behaviors and properties. I'll draw another picture when we get for that. But it can pass everything about it onto child objects, just like a human child inherits from their parent. But I'll use this picture. A square is a special case of rectangle, right? So all of this stuff about a square, all of that could actually come from a rectangle object, because the perimeter is really a property of a rectangle. You know, the color, whether we fill it in or not, if we're showing it, that's actually a property of a rectangle. The area is a property of a rectangle. So the only thing that's actually special about a square is that all the sides are the same length. So it'd probably be a better model to make a rectangle object that had all this stuff, had the length and the width, and then all these other properties and behaviors that a rectangle shape that we would need from a rectangle shape and find useful in our code. And then the only thing special about a square is we could inherit all of that stuff and just add in the description that the length has to equal the width if it's a square. We don't need two sides. We only need one to define the whole thing. And that's kind of a quick pass on inheritance. We'll see it in a little more detail later. And to go ahead and talk about Python, everything in Python, every single thing we work with in Python inherits from this, it's like a grandparent object called object. So everything we work with is an object, and it inherits certain things from this overriding master object, or with the parent-child relationship, I like to call it the grandparent object that everything comes down from. We'll see that a little bit more. The third one is, it often confuses people because it's a really big word for a really simple concept. And that's polymorphism. So it seems like a big, complicated word. It really means many shapes. If we check the actual linguistics, the source of all the syllables in the word, it means many shapes. And that's the ability of one thing to behave as another thing. So like on that picture I drew a moment ago, I'll go back to a branch of that general life tree. We have the general form of life, then we have the different branches coming off, like eukaryotes, and somewhere off that's mammals. And what I have, I think I did humans and elephants. So polymorphism is just the ability of one thing to behave as something else. Because a human has some distinct properties about itself that make it human. So with what's drawn here, there's nothing else that could behave as a human. But a human could also be considered just a mammal, or a human could be considered a life form in general. So polymorphism is that ability. It can act like something else. An elephant, if we need elephant-specific stuff, we kind of have to use an elephant. But if we need any mammal, an elephant would work. And that's the idea behind polymorphism. It's just when we create our objects, each object can behave as something else. Like with these pictures, the rectangle and the square, a rectangle could behave like a square, because the only difference was that length and width side are different numbers in a rectangle. So if we fed the same number into both the length and the width, it could pass as a square. And that's what polymorphism means. I think the big thing that confuses people is just it's a big word. It's a big, complicated sounding word, but it it covers a very simple concept, which we'll see an example here shortly. So these were just quick sketches. I'm going to go ahead and erase these. Is that okay?
Yep, go ahead.
And does that make sense? Those three concepts?
Yes.
And hopefully you see how it's like we think anyway. Like everything we need is included. Let's use a car example. So I brought that one up. Everything about that car is included in it, right? When you buy a car, there's an engine in it, an engine under the hood, there's tires on it. It's ready to go. Hopefully the gas tank's full. When you first buy a car, everything you need for that car is included there. And inheritance, car is a broad spectrum of things. I have lots of different types of cars, right? Like sitting in my driveway right now, I have my old Ford Ranger, which hasn't completely died, but it's an old one. The odometer quit working at over 300,000 miles, and that was like 6 years ago. So it's got to be pushing 500,000 miles. So it's time for a new one. So I also bought then went and got me a Jeep Patriot, which are very different things, but they're both types of cars. And that's the polymorphism, because both of them inherited those properties of what we would think about a car in general. Has tires on it, a gas tank, an engine, all those parts to make it run that belong to the car itself are inherited properties in my Ranger and my Jeep Patriot. And the polymorphism is, if I just wanted to say car in general, jump in one of them and drive to work, well, either one of them can fill that car need. They can behave different. So it's kind of the way we think about stuff naturally as humans, the way we naturally categorize things. Okay. The next thing I want to put on the board here was, I threw the words out just a moment ago, the open-close principle. And that's objects are open for modification I gotta grab a different piece of chalk. Open for modification. But, whoops, I said that wrong. I am sorry. They're not open for modification. Open for expansion. But closed for modification. Sorry, I started to say that backwards. So once we create our object, we kind of seal it up. Obviously, it's computer code. We can just open that file back up and edit it if we needed to. But typically, once we have it, we're happy with it. So if we need more properties, we implement this key concept, the inheritance, and make a child of the object that encapsulates everything we need, and expand that child to have any properties or behaviors that we might need. So some like customization, really. We don't customize. We don't mess with the original. We make a child of the original and customize that child. Oh, I put another example here in the notes. I was talking about the car one. But with encapsulation, another great example of that I forgot was in the notes is computers themselves. What we're here at school studying, right? You guys and girl, I believe she watches the videos later. You all know you're here studying computers, you're learning more and more about them. But the average user doesn't know a lot about computers, right? The average user knows how to power it up, type in the keyboard, move the mouse around, and that's probably about it. It might as well be a little magic box as far as most people are concerned. And that's encapsulation. Everything that's needed for everything that computer needs to do is included in the computer. I mentioned earlier, my next purchase is going to be a Chromebook because I want to sit down for like a month or so, spend like a month and really familiarize myself with the Chrome OS, because I keep seeing questions about those and they're getting more and more prevalent. So I'm kind of in a position that I need to be able to answer those questions. So I got to take a month and do that. But for most people, you run in Walmart, pick the color Chromebook you like off the shelf and open it up and it's ready to go, right? They don't need to worry about how it works. Everything is included in it. And that's just kind of an example of encapsulation. Or, well, y'all are here studying IT stuff. Do y'all know how a key press works? Right? If I come over here and open up the chat room, and if I push the G key a bunch of times, and then the enter key, the letter G showed up. But the G is a physical thing. The operating system is completely a virtual thing. So do you all know how that physical change of the G key made it translated into the virtual operating system thing in order to put that letter in the chat room there? Probably not, right? Because that's electrical engineering, right? What we typically would call computer field, any of the computer fields, we buy a completed keyboard and just plug it up to our machine. And we don't worry about what goes on inside of it because electrical engineers already put that together to work. If you're wondering, this is mostly a capacitor. There's two metal plates that when they get close to each other, there's like electricity flowing through there. And when those plates get close to each other, it creates an electromagnetic field, which is actually a stable state. When a nice smooth field, you think of an EM field like rays of sunshine, that nice feeling of warmth you get out in the sunshine. We create that, and it's a stable state, so the electricity stops flowing. So there's a signal constantly going to the operating system. And when we push the key down, these plates come close enough together to form a capacitor and make a nice, stable electromagnetic field. And at that point, electricity stops flowing, and the virtual operating system notices electricity stops flowing. Just in case you were curious how that works, since I brought it up, that is one of the methods. There's different ways that keyboards work. That's the most common one anymore. That's the nice, quiet ones like we see on laptops and stuff, the very soft keys. Most of them use capacitors anymore, but for the most part, most people that type on a keyboard have no idea how that works, right? Even computer experts. If we need a keyboard, we go buy a finished keyboard and plug it up. We don't really make one from scratch. Unless you're like me, one of my favorite hobby things is to try to create new input devices. Because, well, like the keyboard example, that is a terrible shape, right? I think everybody's heard of carpal tunnel because it is a very, very prevalent problem in our society, right? That's the tube that all the nerves from your hand run through. And if damage happens to that tube, your brain basically receives a pain signal constantly. And that happens a lot in our society because the keyboard damages it. So just using a keyboard tends to damage that. We're going to talk about that at some point too. I always like to give a lecture about ergonomic stuff and keeping that things in mind. But a little bit of a sidetrack, just the idea of encapsulation. everything we need is included. We don't necessarily have to worry about how it works. And that's the main one we're going to look at this level. The first start in object-oriented programming is encapsulating things. So when you all are doing your homework this week about object-oriented stuff, just try to keep that in mind. I believe there's like a car object. So think of a video game that you would put a car in, because this textbook, I'm pretty sure, copied the homework you have to do. I'm pretty sure this textbook copied it from the standard example that comes with the Pygame engine. So think of that car object you're going to create in a video game. Everything you would need in order to use a car in that video game, you want to encapsulate, and think about it that way. And I keep mentioning video games. That's where it really started making more sense to me. Because when we start putting programs together in like a video game format, it's a whole lot easier to think of like every character and prop in that game as its own independent thing. And I know for me, that really helped to understand object-oriented programming. So now a picture to explain these. I like the donut picture for objects, and to kind of represent encapsulation. So in this inner circle, well, here's our object, and then there's going to be some sort of client using that object. And the two circles is a nice example, because the stuff in the inner circle is things we want to protect. So there's different words. I'm going to put the words property, the properties about our object, like the color of it, the numbers associated with it. Well, when we get to examples, we're going to use do animal examples. So we're going to have things like a name, a weight, an age, and all the properties about the thing we're representing. And we want to keep that data safe. So we encapsulate it in this inner circle so that our client cannot access the actual properties. And our outer circle is where we put our behaviors. That is like our functions. So this is our attributes, or we call them attributes when they're in objects, but starting out here, this is our variables. This is all the variables we put together about our object. And then behaviors is all the methods or functions we put together about our object. So if the client needs something from our object, like wants to know what the name property is, it can't access that directly. The client can only access the behaviors, and then the behaviors have access to that internal data. And that's just the important thing in encapsulation. We'll see that some languages we can declare all this stuff to be private, so it's completely private. In Python, we don't really have a private option. There's something we do, and typically we can still access it directly, but it's pretty much standard for programmers to not access something directly if it's in that inner circle. We do that with double underscores. We'll see that in a few minutes, but it's fairly standard. The programmers just respect each other's program, and if something has the double underscore, which is actually semi-static, we all treat it as if it's a private variable, and just use the behaviors to access it. Okay, so I had a note here about the key press thing, which is wrote sideways on my notes, so it must not have been from the first time I gave the lecture. But we are in the computer example, we're the client who can access the pushable property of the key. We can reach over and push that key and make things show up in the chat room. And that behavior, it carries out the actual property of the key press, right? Like, if I come open the, go back over here to the chat room, when I reach over and push the J key, all I can access is the J key. I can't actually access what the software does with it. And same thing with the enter key. All I can do is access the enter key, and then the operating system and the Zoom app do a bunch of stuff on their end that I don't have direct access to. And from that enter key push behavior that I did have access to, it put those letters into the chat room. Which some of this might seem kind of odd. It's something that, yeah, a very active subject, learned by doing it. I'm just kind of talking about this at first, and once we get to some examples, it'll maybe start to make more sense. But it often takes people a little while to get used to. So we're just introducing it here. And it might seem like a struggle when you put your homework together and even, get several completely object-oriented programs up and running, but it might still not fully click. And what I thought helped me the best was video games, because there it was really easy to picture and visualize and understand everything in that game as its own independent object. Which is why I used, when we did the, went over to pip to install new modules, that I used the Pygame engine as an example for that. So what else do I have here? Every property and behavior needs to be built in. So we talked about that. And then in such a way that the client can access what it needs for that object to carry out its job. And one description I've heard of this, which kind of made sense, it kind of helped, it didn't fully get me there, but maybe it'll be helpful for you, is think about it as in terms of language, the way we talk. So an object is a noun. We can make this a whole sentence. So the object is the noun, and every adjective or adverb that we would use to describe that noun, right? The big, tall, red, squishy, every adjective, adverb, anything we would need to describe that is a property. And then every verb that that noun could do, right? The run, jump, fall, every verb that could go with that noun is a behavior. So you could think of it almost like that. Well, maybe not a noun, like a sentence. An entire sentence enclosed in one noun. So we don't have to start looking for different descriptive terms. Those are the properties, and they just come with that noun when we need to use it in a sentence. And same thing, we don't have to go around figuring out what verb to use to put a sentence together. The verbs are the behaviors that just come with that noun when we want to put it in a sentence. That was a description I heard once. It kind of made sense. I don't want to disclude it, because years after I first heard it, it made a lot more sense. But everybody thinks a little bit different, so I wanted to make sure and share that one with you. Do I got enough room for this last little board of notes? Yeah. So that's encapsulation. All this is stuff about encapsulation. And inheritance, the main thing I want to write up here is there's lots of terms for it. Lots of technical and correct terms. There's more than one way to say it. So we have a base class is one of our terms, and a base class extends to a derived class. Those terms usually go together. A superclass is going to can be extended, the expansion or the inheritance. So like a derived class inherits everything from a base class, and then we add more details in. We have superclass and subclass, and parent class extends to a child class. These are the ones I'll use most often, the parent and child. But in lectures, I'm going to try to remember to throw in super and sub and base and derived for the inheritance. But again, at this level, we're not going to be looking at the inheritance or polymorphism a whole lot, mostly just the encapsulation properties, or encapsulation concept, the ability to enclose everything we need about it. There are all sorts of terms, and they're supposed to go together this way. But if you said the child of a superclass, most programmers would know what you're talking about. Right? As long as this side goes with something from this side, other programmers would understand what you're saying. But I'll mostly say parent and child because that makes the most sense in my mind. If we use those words, we're talking about inheritance, which is something that happens a lot all across humanity. So it kind of makes sense with the parent-child terminology. So polymorphism, we're not going to get into that a whole lot. I mentioned it earlier. It's the ability of something to behave is another thing. I use those obvious examples like the categorizations of life, where a human could also behave as a mammal. Right? If we needed a human on that chart that was drawn earlier, the human was the only bubble there that would work. If we needed any old mammal, a human would work for that, or so would an elephant. Or if we needed just any life form in general, well, a human would count there, so would an elephant, and everything else that was drawn on that chart earlier. Yeah, we won't look at it a whole lot. So that's the obvious example, but there are other more subtle cases too. It's hard to come up with a very generic subtle case, but one that I often try to use is you think of an object that does averages. So we have this object that the stuff about it is it's an average object. All it does is find averages for us. So it's going to have a couple behaviors in order to find that average, right? One of those behaviors is going to be add a bunch of things together. And then the other behavior is going to be divide by the total number of things we added together. And that'd be enough to find an average. But for polymorphism, we could use that someplace else. Like that behavior that adds numbers together, we could just go ahead and use that anytime we needed to add numbers together. And that's how polymorphism applies. That object had a method to add numbers together, so we could use it anytime we needed to add numbers. And yeah, I know that's a bad example. I was trying to think of something very basic and simple to grasp, and that example is probably kind of bad because our adding using the plus sign is going to be easier than that in any case, but hopefully that makes sense. We have that behavior in an object, so we could use it in other situations. Okay, so now we're up to Python stuff. 654. Is it okay if I erase the board and get started into Python specific stuff?
Yeah, you're good.
All right, so Python. Everything about Python is an object-oriented language. So what we're going to look at here in a few minutes, we're going to look at classes, which is a very formal, rigid way of putting objects together. But y'all remember a couple weeks ago when we were talking about methods and we talked about modules, and we put together some file of, with a bunch of our own functions in them, right? We'd like define, I don't know, M1, some method, all that stuff, define M2, and we called this like, I don't know, R module or R mod.py. And then when we went to another script, we could just use those. We'd start off by saying import R mod, and then we have access to all of these, right? And somewhere in our code, we'd do something like R mod dot M1, and this method that we wrote over in the module ran. Everybody remember doing that? Something like that. So that is an object. That is an object, but there's a more rigid way to put an object together. That is a very customizable object. It's very specific. And when Python was first wrote, that's how they put the objects together, thinking everything was going to be objects. So just went ahead and did everything as an object this way. But most of our other languages use what's called a classes. We're going to talk about that in a moment. I'll write it over here. A class, which is a blueprint, and we make our objects off of blueprints, which we'll talk about in a second. So Python also, along with our modular type objects, we also have class type objects. And that's what your homework assignment is this week. But I just wanted to make sure you're aware that whenever we import the object, that is an object. And typically, when we start doing the blueprints and the classes, we'll add a class into that other type of module. So it's like extending that object to include some methods and other objects inside of it. And to access things inside an object, we'll use the dot operator. But that is coming up in a second. So Python, everything's object oriented. So like those, we drew trees. And one thing about trees is trees do have a root. So there's this thing called object, which everything else in Python inherits from. I like to think of it using the parent-child terminology for inheritance. I like to think of it as object is the grandparent. Everything comes down from object. Or the ancestor. It's way back to the family tree from all the objects we work with. But it is there. And it's a class, which we'll talk about classes in a moment. It's the blueprint that this comes from. When we say an integer, we have a float, we have a string. Those come down from objects. They're all objects. And they inherit certain properties. I'm going to put 4 on this list here. And there's more that it comes from, but some of them get a little complicated, a little beyond the level we're at here in any class that has the term introduction in the label for it. I'm going to erase this. This was just a reminder about our modules. The way we would import and use modules, we will do the same thing with our classes. So even though everything is objects in Python, we're really talking about our class structures and instances of classes in this lecture, which is just a technicality that might or might not pertain to where you're heading in the future. But really, we're talking about classes. So all of our classes, when we go to create our own, are going to have several methods. One of those is new. And everything we inherit from object will start with 2 underscores, have a name, and then 2 underscores, and then parentheses. So all of these behaviors that we inherit, that our classes inherit from the object class, start with 2 underscores before the word and 2 underscores after the word. And then that is the symbol we'll use to say something is private when we get to our examples here in a few minutes. And this one, I went ahead and put this on there because if you start looking into reference, other online reference material or something, just in case you see this, do not mess with this. Do not mess with. I have seen in reference material, pulled it up, and people will start manipulating the new method about their classes. And if you see that in an example online, go find another example. It is a very bad idea to modify it. At this level, yeah, don't mess with it at all. And in the long run, even when you really know what you're doing, it's still a very, very bad idea. So if you see some example or something where they mess with the new method, look for a different example. The other 3 we will use. So another one is underscore underscore init, short for initialize. And this is what we initialize this. So use this to pass in values. Use to pass in values. We'll see this. This will make more sense when we see it in the example, but the stuff we need to start with. So we're going to do animal examples after our break and create some animal objects. So like say, we create 2 dog objects, they're going to have different names, right? Call one of them Fido, one of them Sparky. So the init method, I'll put a ... here because there is stuff that goes inside the parentheses on that. There's always at least one thing that goes in there, but we'll get to that in a minute. But things do go in there. And when we create our dog objects to use in the examples, one of them will pass in the name Fido and one of them will pass in the name Sparky or something, and that will fill the name property. So this is what we use to pass in values. Another one, which we have actually used extensively, underscore underscore str underscore underscore. This is what we use for a default string. A default string representation. So this is something that we inherit from our object. So everything in Python has this. So some code I'm going to erase here in just a second. Let's say x is 3, and then we go print r num is plus x. We've all seen the error that's going to throw a few times, right? Can calculate a string together because x is a number. What's the Python interpreter going to tell us when we try to add a number and a string together? It's going to interrupt what we're doing and say something, right? So we always have to call, we've been calling this method str and pass x in to cast it as a string. And that actually calls this internal underscore underscore str underscore underscore method, where we put what a default, well, somebody else did it for an integer. Somebody else told it what a default string representation of an integer is. But on all the objects we make, we want to make sure and have that same thing. We're going to print some output. Even later when we're seeing nice fancy GUIs, and it's not going just printed to the console, we're still going to have some string sort of output. So that's an important one. We always want to include that. So init and string, every object we make, we want to make sure we'll have that. Well, we can't make a class without initializing it, but we want to make sure there's a way to turn it into a string, a way to output it. And when we get to the examples, I'll show what happens if we if we don't include that. So that's just a default cast to a string, a way to represent it. And well, printing isn't the only thing we've done with our numbers, right? At least this example, that's something we've seen many, many times. Maybe once we put a value in x, we're going to do something like this. If x is less than 10, we need a way to compare things, right? Or in particular, our most basic comparison, just the yes or no comparison. Is x equal to 10? We want to make sure and have that as well. So we also want to include in all of our classes an underscore underscore EQ, where we define what equality means. Excuse me. Define what equality means for our object. Which again will probably make more sense when we see an example, but well, we're going to do animal examples tonight. One of those is a dog object. I used that already. We have two dogs. One of them is called Fido. One of them is called Sparky. So we're going to want a string method so that if we say print that, we'll get the different print statement, right? We'll print out this dog is called plus whatever the name we passed in is. As just a default way to print that value. But there's also equality. How are we going to define what it means for two dogs to be equal? The same weight, the same name, right? And this is something that takes a little more thought, and there's not a hard yes or no answer. But if we think about different dogs, right? If let's say Fido's a Chihuahua and Sparky is a Black Lab. Well, could we look at the breed of, for equality? Do we look at the breed of them? Do we look at the weight of them, the age of them, the name of them? What do we look at in our object to determine what counts as equality with other objects? And obviously that's something there's not a right or wrong answer to, and it's going to be different in every single one. It's just something we have to choose. That way we can use our object in selection structures. And there are more of those, but these three are the ones we need right now. We want to make sure and initialize it, have a way to cast it to a string, and at least have the yes or no comparisons. So start with equality. We could extend that and write methods to determine when something is bigger or smaller. But for starting out, let's just go with the simple yes or no. Are those two objects equal? So we want those three. And I just included this one in the list to mention do not mess with the new method. So if you're looking at examples online, and come across something where they alter the new method, go find a different example. That is that when you change that, you have to change what the interpreter, how the interpreter processes Python, which is way beyond the scope of this course. But some people still do that. Like in our compiled languages, a compiler is just a program that was written. We can rewrite a compiler. We can change it and customize it any way we want to. And if you start messing with the new thing, everything we have in Python, and here's from a bunch of stuff from object, and one of those is new. And if you go messing around with that, you might have to change the interpreter, which is a very complicated thing. So I just threw that on the list to mention, don't mess with that one if you see it somewhere. But it is there. We have access to it. We're programmers. We tell a machine what to do. But some very, very good computer scientists have refined that one. So you can trust what they put together and then what they put in the interpreter to do. So just roll with it on the new method. And everything has the init, the string, and the equal. Those are the most basic things we'll need to work with. There's other ones, but those will come later. For us, just getting started in object-oriented programming. And what time is it? 7:12. So seems like a good time to take a break, right?
Sure, yeah.
Any questions about that? The general concepts?
No.
Okay, yeah, and it's a very active subject. So those are just kind of some pointers, some words to rattle around in your mind. When you start doing it, it should make a little more sense. So why don't we take 10 minutes here and come back at 7:23?
Okay.
Will that be enough time for you to get the cooking, Tom?
Yeah. I've been running back and forth, so yeah, of course for me.
Okay. We'll see you all in a few minutes. I need to go. I'm getting very thirsty.
Okay.
I need to